Okay, hi everybody. I'm trying a new set of headphones. I found that the noise canceling was a little crazy, but okay. So welcome everybody to our next lecture. This is one related to probability, or as we said here, the language of uncertainty. How beautiful. In this lecture, we're going to build the conceptual foundation that connects probability to everything else that you'll do in this course. But I wanted to start with a story. I heard this years ago. Actually, I think I was getting my PhD, and I used to listen to a ton of podcasts as I was doing data analysis. And so one of these podcasts was a show called Radiolab, and they did this uh, really fun episode on stochasticity. I'm going to check something really quickly. I just want to make sure that my headphones are connected because they're new. Okay, they are. The Bible thing. Okay, there we go. Perfect. I just wanted to check. Okay, so here is the story. Okay. In 2001, a 10-year-old girl named Laura Buxton, she was living in Staffordshire, I think, England, decided to release a helium balloon from her yard. She attached a note and it said, "Please return to Laura Buxton." And she gave her address. And so the balloon traveled, I think, like 140 miles, landed in the yard of another girl who was also named Laura Buxton. And she was also 10 years old. So of course they start a correspondence because they're 10-year-old kids in the 2000s and they've had this like really weird coincidence. But when the Lauras started to kind of meet each other and talk things through, they had all of these other similarities. So they were the same height, they had the same color hair, they were both wearing nearly identical outfits, pink sweaters and jeans. They had they both had a Labrador. It was black, and they both Labradors were 3 years old, and then they both had a pet gray rabbit. So they, of course, thought this was a miracle. Is it a miracle? Um, is there some kind of evidence of aliens coming down and messing with us based on this information? Or is it something that probability can explain? So here's the thing, the big punchline of this whole scenario was the fact that a couple of things are going on. One, we have the tendency to notice coincidences that happen. So we have a bias towards it. We don't notice all of the millions of things that could have been coincidences but weren't. So they had things that were not in common, right? Maybe their parents were different ages or their houses were different colors. There are millions of things that were not coincidences. Um, and then there's this other concept, the one of just large numbers. So every day, an enormous number of events happen to billions of people. And the number of possible coincidences is actually staggering. It's huge. And so when you have that many opportunities for something surprising to occur, it would actually be weird if we didn't have surprising things happen, if we didn't have coincidences. So this is an example that kind of allows us to understand what probability is trying to help us formalize. Not whether a specific coincidence is meaningful, but whether we're seeing a pattern that is surprising, given how many opportunities exist for it to arise. And that way of thinking, comparing what we see to what chance alone could produce, that is at the heart of statistics, especially, and this whole course. Really, it's for Bayesian and frequentist statistics, but that's at the core. Oh, so again, that was a really fun show. If you want to see, if you want to listen to the whole thing, they go into some other fun things about the random nature of coin tosses and everything else. But it's a Radiolab, and the episode is called Stochasticity. Okay, so probability isn't just a topic in a statistics class. It's how science communicates uncertainty to the rest of the world. And when we misrepresent it, it has real consequences. So, one of the classic examples that I'd like to point out really came from my time when I was first starting my PhD project and I was focused on climate change. So, the IPCC had some kind of statement on climate change. It might have been something like, There is a greater than 95% probability that human activities cause the majority of observed warming. What does that mean, though? Like, it was hard for people to understand. People have a hard time kind of internalizing what probability means in many contexts. So, it didn't mean that scientists were 95% sure. It didn't mean that 95 out of 100 scientists said that this was happening and others weren't. It means that across the range of analyses, if we repeated our models hundreds and or thousands of times, 95 to 100% of them showed some sort of human influence exceeding natural variability on the climate system. So it's really more of a statement about data and the way scientists go about quantifying uncertainty in these kind of multiple. Oh, hello.
I'm sorry.
I'm sorry. I'm like giving a lecture.
I'm sorry. I don't have any news. Sorry.
Okay, no worries. You probably need to go to the science annex. You're welcome. I think it's weird how people just walk, the door was closed. I don't know. People just walk in. We're lucky I'm not in here naked or something. Ah, okay, so rather than starting over with this whole thing, I'm just going to keep going. Sorry about that, though. I should probably lock the door. Okay, let's go on to a couple of other examples. So think about the weather. We get this all the time. If a weather forecast says something like there's a 30% chance of rain tomorrow, does that mean 30% of the area gets rain? Does it mean that rains for 30% of the day? It doesn't mean either of those things. It means that among all days with the similar atmospheric conditions, if you're running these models over and over again, about 30% of them produced measurable rainfall. So this again connects back to this long run frequency statement. And we're going to get into how that kind of forms a lot of our statistical understanding here and then in subsequent lectures. Okay, in conservation, this is one that's very close to my heart, and some of you might actually do by the end of the semester. Uh, if a population, we estimate something called population viability. And if a population viability analysis tells us that there's a 0.4, 40% chance, a 0.4 probability of local extinction within 50 years, that means if we ran the current environment, the current population sizes, thousands of times under the same conditions, roughly 400 of those, like 1,000 runs, would result in extinction. So again, that's how we're kind of getting these probabilities because we recognize and integrate these elements of chance in some of these systems. So the the point is that we often have the need to think and talk about probability. In the original iteration of of this, I went into some really crazy calculations of probability. I think it's fun. We're going to go over a couple of main examples. The I use this most honestly when I was doing genetics. So, and you would be calculating kind of deviation. I use probability, I should say, to look at like deviation from the Hardy-Weinberg equilibrium and things like that. So we use it in the biological sciences, but really forms kind of the foundation of statistics, which is why we're going over it first. Okay. Before we get into some of the mechanics and basics of probability, I want to make sure that we are on the same page about a word that often causes confusion, and that is error. So when we're talking to each other in everyday language, error means a mistake. But in statistics, error refers to the difference between a true population value, again, the statistical definition of population, whatever it is we're measuring and we're interested in, the true population value, for instance, it could be the actual average height of all giraffes, and the value that we estimate from the sample. So it's the difference between the true population value and what we're actually estimating from our sample. So we don't consider this difference a mistake. It is the inevitable result of the fact that we're measuring a piece of the system. We're measuring a sample, not the entire true population of giraffes. So statistical models are designed to separate the signal the systematic pattern that we care about, like treatment effects or relationships between variables from this background noise or error. And that's a key insight. Error is considered unavoidable, and statistics doesn't kind of deal in certainty. Instead, it replaces this kind of certainty around our parameters with probability. So every conclusion in statistics is a probabilistic one. Um, it is just a way, really, of looking at our sample and saying, how sure are we that we are getting a mean, a value, a pattern that is real and not due to chance that is introduced by the need for us to sample. So we'll go over this again because that's key for understanding what the p-value is telling us when we run a statistical analysis. Okay. So here we go. The central question in statistics, and really the question that connects this entire course, is could the pattern I observe have arisen by chance alone? Could the pattern I observe have arisen by chance alone? And that's it. The single question is the engine driving almost all statistical tests that you'll encounter. So you can imagine as like, did the difference between treatment and control happen because that treatment actually worked? Or could it have arisen due to random variation inherent in the sampling process? And so that's how we're applying probability. We're using it to answer that question. One of the key things that we do when we're thinking about probability, and this is particularly true when you're calculating different probabilities, using data, or you want to define something, is that we start by defining the sample space, and that is the complete set of all possible outcomes. So this might seem obvious, but defining the sample space is really critical, because if you get the sample space wrong, everything else that follows will be incorrect. So the part that matters most for ecologists when your question is like your question that kind of links to your sample space. So if you're looking at these two different areas up here, say we're asking, is a species present? Your sample space is presence or absence. There are two outcomes. That's a binary question, and it leads to things like logistic regression and occupancy modeling. There are two possible outcomes there. But imagine, on the other hand, we're looking at the second panel here. We're asking, how many individuals are there? That sample space is 0, 1, 2, 3, it could almost be infinite, right? So that's a count question, and it directs us to use a different statistical test, in this case, a Poisson or a negative binomial model. And we'll get into all of that and choosing those models later. But yeah, these different questions that we're posing lead to different sample spaces, and then this results in us using different statistical frameworks. So that's a pretty key understanding. This idea that probability is a long-run frequency is something that is at the heart of statistics. What does that mean? Suppose you had 100 seeds and 30 germinate. You estimate the probability of germination at 0.3, right? But does that mean that every time you repeat this experiment, exactly 30 of the 100 seeds will always germinate? No, that's not what that means. It means if you repeated this experiment many, 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 many times, the proportion of seeds that germinate would converge towards 0.30 on the long run. Any single trial might give you 25, 33 germinants, 28 germinants. The estimate is really noisy, especially when you have few observations, but it stabilizes as you collect more data. And so this is a key thing too, that we'll get to in a second. I wanted to point out that the R code in your tutorial simulates this process. So in it, we can envision that we're flipping a coin something like 2,000 times and we're tracking the proportion of heads. So early on, you might see something like the first 10 or 20 flips, the proportion swings around wildly. But as the number of flips increases, the line settles down and you start getting the true probability of a 50% chance. So with a quote unquote true coin, one that's not like weighted in any particular way that would make it land on heads or tails more frequently, you're expecting that on these long run frequencies, it's a 50% chance of getting either heads or tails. So you can run this code yourself and you can see this in process. We refer to this as the law of large numbers. When we get more and more and more and more data, the more data that we have, the more closely we can get at estimating the true population values. And this is why sample size is so important. So we always talk about sample size, especially when we're designing our experiments and thinking that through. This is part of it. The larger the sample size, the more the better we are at being able to kind of estimate the true statistic that we're interested in. And the reason we can't have infinite number of samples, of course, is because we don't have the money, time, or capacity to do it. So we're always running up against that tension. How many samples can we have? More is always better, but realistically, what can we do out there? Okay. So one really key thing to know is that small samples are noisy. I'm just reiterating this because this is a key thing that relates back to how we develop our sample sizes. So this is just an example of that. Suppose the true germination probability is again 30%. You only plant 10 seeds. You might see anywhere from 1 to 5 germinate. Your estimate is going to be all over the place because you have a really small sample size. With 50 seeds, you'll typically see somewhere between 10 and 20 germinate. It's better, but it's still noisy. But then when we go up to 500 seeds, your estimate narrows to something like 135 to 165 individual seeds germinating. And that's a much tighter range around the true value. So again, your example in your tutorial is something that kind of hits that and kind of hits that section that kind of hits this message home where you can really see it in action. So do the tutorial. Okay, I wanted to take a brief moment to talk a little bit about conditional probability, mostly because we see it in different ecological systems. And so I wanted to be clear that we have all of these different ways that we can go about calculating probabilities and thinking about it, estimating the sample space, thinking about the actual likelihood that things happen. But I wanted to give a shout out to conditional probability because we use it a lot in ecology. So conditional probability describes a situation where the probability of one event depends on whether another event has already occurred. It's written as the probability of A given B, and it captures the idea that knowing something changes what we expect. So an ecological example is looking at seed production in plants. So imagine that we tagged something like 200 perennial plants in a population over the winter. Some survive and some don't. In the spring, you're going to record the number of surviving plants that flowered. And then you can take that farther and look at seed production. So there are different questions you can ask, but what we typically do is we break this down into different dependencies. So we might say, okay, what is the probability of survived? If survived, what is the probability that it flowered? If it flowered, what is the probability of producing this many seeds? And so this is one of those things that kind of that is kind of important to the sciences, especially for looking at populations, which some of you might do later. So yeah, stage structured population models, life tables, all of these things all really, really are dependent on this kind of concept of conditional probability. So I wanted to give it a shout out. Okay, another thing that is really at the heart of being able to understand probability and statistics is this understanding of independence versus dependence. So notice that it's very connected to the conditional probability concept. There are two events that are independent. When there are two events that are independent, knowing one tells you nothing about the other, if that makes sense. So mathematically, the probability of A given B just equals the probability of A. The conditioning doesn't change anything, but they're completely independent. They're not affecting each other. So for example, we could say that the survival of two plants growing really far apart in a similar habitat is probably approximately independent. And we do this a lot in ecology. When we're developing our sample size, we use space as a proxy for independence. And that's because if you're kind of far apart, there's really little chance of you being able to interact. Now, many of you are probably familiar with Claire's work. She does a lot with pollinators. When she's there thinking about independence, what do you think she does? Like independence between plants. She thinks about the longest distance a potential pollinator could fly in like a given day. So that is going to, she uses that minimum distance of flight to determine how far apart she needs to have her samples being. Because in theory, this population over here could be really influencing this population over here if those pollinators can make that jump. So that's another example of thinking through how we define independence, but we are also often using that spatial proxy. Okay, now let's turn. So we're thinking about the survival of these plants. The survival of those same plants across consecutive years is almost certainly not independent. So if we're measuring the same individual over and over again. So a plant that survived in year one is probably healthier, bigger, and a favorable microsite. These are all things that increase your chance of surviving to year two. So this matters in statistics for several reasons, but principally, many statistical tests assume that your observations are independent from each other. And if they're not independent, if you violate that assumption, for example, by treating repeated measures like the survival, tracking the survival of those individual plants, as independent data points, your results can be very misleading. And we'll go over this more as we get kind of into statistical testing and assumptions. So this is one of the most common mistakes in ecological statistics, is not taking into account independence or lack thereof. Okay. So let's do a little switcheroo. We've built up kind of a vocabulary around probability. We've talked about sample spaces, long run frequencies, and conditional probability and independence. So now let's see how all these things kind of come together to form the basis of statistical inference. Okay. Up to this point, we've been talking about the probability of individual events. Will this seed germinate? Will that plant survive? But in practice, we usually care about the distribution of outcomes, not just whether one seed germinates, but how many out of 50 will germinate. A probability distribution gives us the complete picture. It describes all possible outcomes and tells us how likely each one is. So here's an example. Say the probability of germination is 0.3, so 30%, and you plant 50 seeds. The expected number of germinants is 50 times 0.3, which is around 15. But you won't always get 15, right? We've talked about that. So sometimes we'll get 12, sometimes we'll get 18, occasionally we'll get 8 or 22. And what people do is they look at this and they simulate this process of germination or whatever the event is thousands and thousands of times. And when you repeat this process, like this kind of random process of germination over and over and over again, you get this histogram. For many processes, things that are like continuous in nature, you often will have this bell-shaped curve. So in this case, we'd have this bell-shaped curve centered around 15. It's showing the full range of plausible outcomes. And because this is an occasion where a seed can either germinate or not, there are two choices, we would refer to this distribution as a binomial distribution. And so it tells us what normal variation would look like for this particular process. I'm going to go over this again and again, probably. So this is a big deal. A probability distribution tells us what model, gives us a model of what we can expect under specific conditions. And once we know what to expect, we can ask whether our actual data look like they came from that process or whether something else is going on. So keep in mind, like what we would do in this germination thing, we wouldn't say, we We wouldn't add in a treatment that is supposed to increase the likelihood of germination. We're just going to say, if this is completely random and we're getting this 30% thing, this is what we would expect. We would expect in 1% of the cases, we're going to get 8 germinants, but in the majority of these runs, we're going to see around 15 germinants. So we'll look more at probability distributions in a bit. So what I've described in that previous slide is a null model. This is a really important concept. A null model is a probability model that represents the hypothesis of no effect. Nothing interesting is happening. There are no patterns, there are no treatment. Everything we're seeing is generated by chance. You probably know that many of our statistical hypotheses, not the ones we might write up in a proposal, but our statistical hypotheses are often based on this null model. So we would ask something like, we're looking at a restoration treatment and we're trying to determine whether it increases germination. And the treatment group, 22 out of the 50 seeds germinate, and the control, 13 out of 50 germinate. That's a difference in germination rates of about 0.18. It seems okay, it seems meaningful, but could this have arisen by chance? That's what we're doing here. That's the kind of thing that we're trying to answer with our statistical inference. Okay. So let's move on from null models to building a null distribution. So this is where we actually build the null distribution using a permutation test. And here's how it works. So step 1, depending on what we're looking at, we would combine all observations into a single pool, and we ignore where they came from. We're going to ignore the treatments and the different groups and everything because we're thinking about things arising from random chance. In step 2, we would randomly reassign the group labels. So just give like this guy over here, he's, I don't know, control. This guy is something else. And the next step, we would calculate the difference between the two groups with these new random labels. And step 4, we would repeat this process tens of thousands of times. So if you look on the slide, the R code on the right is doing this. Each iteration shuffles the group labels, computes the difference in germination rates, and stores it. And after 10,000 iterations, we have a histogram, the null distribution. And this shows the full range of differences that we'd expect if the treatment had no effect. And so what does that distribution look like? Well, most of the values would cluster around 0, which makes sense. If the treatment does nothing, the difference between groups should be really small and random. But our observed difference of 0.18 sits out in the tail of the distribution. That's telling us that it is unusual. And this is exactly what we use to define our p-values. So the p-value stands for probability, which is part of the reason we're talking about this stuff. And the p-value is simply the proportion of the null distribution that is extreme or more extreme than what we actually observed. So it's kind of answering this question. Could I get this value or something more extreme than this value simply by chance? So if a treatment truly had no effect, how often would chance alone produce a difference as large as the one that we saw? And if the answer is that's pretty uncommon, like 2% of the time that's going to happen, then our observation is surprising under the new model. We have evidence that something beyond chance is happening. We are feeling pretty confident that what we see is a treatment effect. So the p-value is not the probability that your hypothesis is true, is not a measure of how big the effect is, and it's not proof that the treatment works. It is a piece of evidence that we use alongside effect sizes and confidence intervals and biological reasoning. But we can translate it to percentages. So what would the p-value be for 0.2%? We would have a p, okay, if we were saying, like I mentioned, 2% of the time, we might see a germination rate as large or larger than the one that we actually observed by chance. So in that case, our p-value would be 0.02, and we would say there's a 2% chance of seeing this pattern by chance when in fact there is no evidence, or there are when in fact this pattern actually arose by chance. So we know that just by taking samples, some percent of the time, we're going to see patterns that really aren't there. And this is the whole reason why we're really focused on using statistical tests, because we want to be pretty certain that when we're saying there's a treatment effect or there's a relationship between variables, that those are real. They're not just because of error and noise in our samples. Okay. All right. So what we were just doing when I talked to you about taking our data set and running all of these different trials, like tens of thousands of trials, what that is a permutation test. And it follows this three-step logic that underlies every statistical test that you'll encounter in this course. One, you build a null model, a probability model that represents no effect. Two, you generate a null distribution, the range of outcomes that chance alone would produce. And step three, you measure surprise, or you measure, again, that likelihood that this pattern arose by chance when in fact there's no real pattern there. There's no real treatment effect or relationship. And that is our p-value. So t-tests do this, ANOVA does it, regression does this, chi-square tests do it. They're all using this basic logic to perform a statistical test, which is why we always talk about probability when we talk about statistics. Okay, here we go. Before we kind of come to an end with this particular chapter, I wanted to briefly show you where the concepts from this chapter will reappear through your course as you kind of work through it. So hypothesis testing is the direct formalization of the null model logic that we just built. Every test asks the same question that we ask: how surprising is my result under a null model? In regression, every coefficient that you estimate has a probability distribution, whether we're talking about testing whether a coefficient differs from zero. That's like saying, like, okay, it's primarily when we're looking at slopes, right? We're saying, we're thinking about whether there's like a positive or negative relationship. And we're saying, okay, is this slope, does it differ from zero? Like, in other words, is there some kind of relationship there? Population viability models use probability at every level: survival probabilities, reproductive probabilities, transition probabilities between life stages. These are all critical and incorporated in our population viability analyses. And so we'll talk a little bit more about Markov chains and what goes into estimating some of these key features of populations. And then, of course, if you ever use Bayesian methods, you'll see that Bayes' theorem is just the conditional probability formula from today applied in reverse. So instead of asking, what's the probability of data given the hypothesis, we ask, what is the probability of the hypothesis given the data? So it's just the same math, but kind of a different direction. You don't need to understand these yet, but I just wanted to point out that we're going to kind of revisit this concept of probability throughout the semester. Okay, so let me leave you with this. Probability does not remove uncertainty from ecological science. It is a way for us to work with uncertainty in a very transparent and rigorous way. And that's in essence, what this whole course is about, and what inferential statistics. Inferential means we're being able to make an inference about the true population based on our sample. That's what this is all about. So we will move forward, and we're going to keep revisiting these themes throughout the semester. Thank you all.